Hello, this is Müjdat from Marmara University, Bennett Research Lab. We will present our work in DECICE project with our colleagues from Bennett Lab and BIGTRI. Yavuz from Bennett Lab will present some work, and Berkay from BIGTRI will present his own work in DECICE project in this interview. I would like to give a brief information about Bennett Lab. Bennett Lab is a research lab at Marmara University focusing on intelligent transportation systems, connected cars and V2X communication, and also we use AI, data science, image processing, not only in intelligent transportation systems, but also in manufacturing. We participated in many Horizon Europe projects like DECICE, and we are contributing in these fields in these Horizon Europe projects. Bennett Lab is the largest university research lab in Turkey, located in Istanbul, with 15 full-time researchers. There are 3 teams working in the research lab. One team is working on V2X communication, embedded software. The second team is working on IoT and networking. And the third team is working on artificial intelligence, machine learning, and image processing. And all these teams are contributing together to these projects collaboratively. All we do is beyond state of the art, and we are happy to contribute to the projects and science like we do in the DECICE project. Thank you.
Hello, this is Berkay from BIGTRI. I am the V2X communication and autonomous driving team leader in BIGTRI, and I'm managing the DECICE project on BIGTRI side. In DECICE project, we contribute in several areas. One of them is the digital twin development. And we are providing our contribution for use case 1, which is vulnerable road user safety in intelligent intersections. Also, we provide some contribution on the DECICE API sites, especially on front-end development and also development of the APIs. So thank you for the interview.
Hello, this is Yavuz Bostancı from Marmara University's Bennett Lab, and I am leading IoT and networking team in Bennett Lab, working here for a bit more than 7 years. And in the DECICE framework, we are providing a use case 1 for vulnerable road user detection. And me and my team are working on the detection models, image processing tasks mostly, and also the network parameter collection metrics and the software that supports that. Thank you.
Thank you. Hello, and thank you for the opportunity to speak out our work in the DECICE project. My name is Müjdat Soytürk, and I'm proud to represent Marmara University and our research group, Bennett Lab. We are a team of researchers and engineers focused on creating innovative solutions in the fields of smart mobility, connected vehicles, V2X communications, and edge cloud computing. In the DECICE project, we lead a use case 1, entitled Smart Intersection with Vulnerable Road User Detection. This use case addresses one of the most important challenges in urban mobility. How can we better protect vulnerable road users, like pedestrians, cyclists, and motorcyclists, especially at intersections? We developed and deployed a complete system at 3 real intersections on our campus, equipped with high-resolution RGB cameras, roadside units, edge computing devices, and wireless access infrastructure. Here, we use deep learning models to detect vulnerable road users in real time, and we share their 3D location and orientation with nearby vehicles via V2X communication, whether the vehicle is autonomous or human-driven. This information helps it make safer and more informed decisions, like slowing down or stopping to prevent accidents and improve traffic flow. Our infrastructure is a living lab that showcases what the DECICE framework can achieve. It supports real-time image processing, digital twin monitoring, AI-based workload scheduling, and multi-cluster orchestration across edge and cloud. In collaboration with our partners, we run a distributed Kubernetes setup, one cluster at Marmara University and another one at another partner in the project, connected with Cilium cluster mesh. This allows us to simulate real-world multi-location intersections and test how DECICE performs under different network conditions and workloads. We use NVIDIA adjacent devices and optimize our models using TensorRT, AP16, and INT8 quantization, keeping inference latency below 300 milliseconds, as required by ETSI safety standards. Thanks to federated monitoring with Prometheus, we collect detailed metrics on GPU, CPU usage, network latency, and inference performance. These metrics are fed into a digital twin that continuously informs our AI scheduler, enabling dynamic, energy-efficient task placement. We also address data privacy, which is crucial in video-based systems. Our detection pipeline includes selection encryption of image regions, protecting identities while preserving performance, ensuring GDPR compliance throughout the system. This balance of security and usability is key to public trust in intelligent transportation systems. To sum up, Marmara University's VNet Lab plays a leading role in designing, implementing, and evaluating use case 1 of the DECICE project. We show how smart intersections powered by real-time AI, V2X communication, and intelligent edge cloud orchestration can dramatically improve road safety and urban traffic management. This work reflects our commitment to not just technology, but to build safer, smarter cities for everyone. Thank you.
So Hoshment is an AI-driven scheduler for cloud workloads, and it can address intersection-related challenges in CITS with real-time decision-making, predictive analytics, and resource allocation. Adaptive learning capabilities of Hoshment enable scheduling decisions to be based on real-time performance feedback, and which allows it to respond dynamically to varying conditions and network fluctuations. And by managing heterogeneous computing sources, which is typically the case in CITS infrastructure, Hoshment supports reliable operation in mobility scenarios. So the DECICE platform supports safety for vulnerable road users by enabling real-time image processing, network-aware scheduling, and an integrated edge cloud infrastructure. Processing video streams at intersections help detecting pedestrians or cyclists or motorcyclists and immediately sending this information to nearby vehicles and roadside units. With technologies such as Kubernetes or KubeH, optimal distribution of processing tasks are done across heterogeneous devices, which dynamically adjusts to real-time network conditions. Also, the DECICE framework employs digital twins and AI-driven scheduler to continuously monitor and predict the performance of the infrastructure. And it allows for proactive resource allocation for real-time and reliable detection of vulnerable road users. And we believe that it would help to reduce accident risks and enhance the traffic flow for intelligent transportation systems.
All of these attributes are actually critical for cooperative and intelligent transportation systems, aka CITS, and they are ensured or maintained by the framework's smart resource allocation mechanism, which we call as the AI scheduler. Basically, the AI scheduler optimizes the node allocation within a multi-objective optimization function, considering the network metrics, node resources, and power consumption. This scheduler is assisted by the network and node exporters. The exporters share the metrics such as the network latency, CPU or GPU utilization, or power consumption, using a singular interface, namely the digital twin. As the framework integrates the high performance computing or HPC cloud and edge clusters, and IoT devices, the digital twin offers a unified and detailed view of the integrated cluster. So this detailed overview is utilized by the AI scheduler using the component so-called the scheduler controller. So the AI scheduler operates collaboratively with the scheduler controller to get the up-to-date cluster metrics from the digital twin. The scheduler controller is also responsible for filtering the nodes that are not suitable according to the user's restrictions. Along with the controller, the AI scheduler filters out the inapplicable nodes for real-time execution of that workload, or for ensuring at least the minimum limits defined by the user. Therefore, the workloads can be deployed on the nodes that are best for fastest processing. On the other hand, the workload might be network dependent. That means it may need a connection with a peer. Within this connection, the user might require a level of reliability, throughput, or latency. In such a case, the network metrics are taken into account. Also, we define a job topology description for mapping the interconnection between different peers. These peers might be two different workloads, or workloads and devices, or they can be external services. Using this topology input and the network metrics input, the scheduler and the controller filters out the unsuitable nodes and executes the multi-objective optimization function. Allocating the best possible nodes for the lowest latency or fastest processing without considering the energy consumption may not be a suitable option for energy efficiency, especially in large-scale clusters, which is very likely in intelligent transportation systems. For instance, when the fast processing is highest priority, the resource allocation would be towards utilizing all of the nodes without leaving any of them in idle mode. This is called the spreading strategy. As opposite, DECICE uses bin packing strategy, leaving as many nodes as idle while occupying resources of the nodes that are already occupied, as long as they fulfill the timely execution of the workloads. Additionally, the idle nodes might be put into sleeping modes, which might further decrease the energy consumption. Finally, I will make some comments on the accuracy perspective. The accuracy is more dependent on how the developer designs the model and how reliable the model works. The model can be optimized for edge devices, which usually have lower resources compared to cloud nodes. As a result, there will be a variety of inferences caused by the optimization for different types of different device architectures. So DECICE framework can handle this variety by mapping different inferences to target device architectures and offloading the processes to higher accuracy models, especially when the accuracy drops below a certain level. Thank you. Okay, it's better to generalize the term intelligent intersection applications with CITS, or cooperative intelligent transportation systems, because DECICE, I think, effectively addresses a significant portion of these challenges in CITS. We see that edge computing is emerging in CITS. This is actually due to the low latency requirements, especially in the so-called advanced cooperation cases. As the edge computing scales, it leads that CITS infrastructures getting more heterogeneous. Heterogeneity means here the infrastructure accommodates a variety of device types and architectures. So the current open source technology stack might be incapable of managing, especially as we think of the CITS services operating on a large scale, because the CITS services operate on city scale, which means they operate on large scale. So addressing the heterogeneity is among the objectives of the DECICE framework. So we can say that it is device agnostic, thanks to the digital twin. So the user interaction as well as the automation of tasks is made easier or more suitable compared to the existing technology landscape, which may require a lot of customization to handle this. Considering the scale of CITS infrastructures, which operates on city scale, the manual intervention or solutions that do not handle the heterogeneous infrastructure will not be sufficient, especially in terms of sustaining the availability of the services. Also, the cluster will run a variety of services. These services might be either independent from each other or they might be interrelated. The solutions should address this interrelation, considering the network might be unreliable or insecure. To summarize, DECICE addresses these challenges, so it is actually a promising tool for CITS services that are operating in the edge cloud environment. It has a variety of measures considering the large scale and heterogeneous infrastructure, unreliable and vulnerable network, and for complex task automation. Because it has an AI-based and network-aware scheduler, a dynamic digital twin, and variety of security features. I think it offers a robust open source framework for CITS use cases.
Yes, one of the most important aspects of our work at Marmara University is that we always approach mobility systems with an end-to-end perspective. We don't just focus on individual technologies or isolated modules. Instead, we consider how to build, deploy, and test the entire system as a whole, from the edge to the cloud, from the infrastructure to the vehicle and back. In line with this approach, we have developed and integrated a wide range of system components, including in-vehicle interfaces and connected vehicle applications like V2X applications, edge-level services, and infrastructure-side applications. We build cloud-based orchestration and monitoring tools and robust communication protocols and performance measurement modules. All of these components are fully deployed and actively running within our campus, providing a ready-to-use real-world testbed. Any scenario we imagine, from emergency vehicle alerts, notification to vulnerable road user detection, can be safely executed and validated in real time within this setup. This is not a simulation-only environment. We have fully functioning traffic lights, real roadside infrastructure, operational edge devices, and cloud services, all working together as an integrated system. This allows us to test not only the AI models or communication layers, but the actual behavior of the system as a whole under different load, latency, and safety constraints. We also developed several digital twin tools that simulate the system behavior and help us conduct virtual tests and vehicle-in-the-loop experiments in a safe, repeatable manner. These digital twins are essential for testing edge cloud interactions, verifying latency under dynamic scheduling conditions, and assessing security mechanisms against simulated cyber attacks or data breaches. Our test environment allows us to inject controlled faults or attacks and then measure the performance and resilience of new security protocols in a safe and measurable way. What's truly unique about our setup is that everything from perception to action can be tested and validated in a safe, repeatable, and realistic manner. This creates a solid foundation for evaluating how emerging applications and algorithms behave when they faced with real-world conditions. To conclude, I would highlight our contribution to the DECICE project goes far beyond a single use case. We are creating and maintaining a living, evolving infrastructure where new ideas can be implemented, evaluated, and improved in a real-world setting with full control, visibility, and reproducibility. This kind of platform is not only beneficial for research, but also serves as a sandbox for future mobility solutions, helping bridge the gap between academic innovation and industrial deployment. Thank you. Thanks for this opportunity.